Ever wonder what a physical circuit board, with all its little wires and chips, and your favorite app have in common? Well, today we're going to pull back the curtain on a really powerful idea that connects them. It's this concept that acts like a universal translator, and it's basically a secret weapon for solving some seriously complex problems.
I mean, they seem like totally different worlds, right? On one hand, you've got the physical stuff, currents, voltages, actual components you can hold. And on the other, you have the purely abstract world of code. But what if I told you they both rely on the exact same problem-solving trick? The link between them is this surprisingly simple and elegant idea about transformation.
Okay, let's think about it like this. Imagine you're at a big international conference. You could have a live interpreter translating the speaker in real time. That's super flexible, right? But it's also a bit slower. The other option? Translate the entire speech beforehand and hand it out as a book. It's way faster to read, super precise, but you lose that live interaction. Now, here's the key. Both the interpreter and the book deliver the exact same meaning. They just change the form to serve a different purpose. And that idea, changing the form without losing the meaning, is at the heart of everything we're about to dive into. And this isn't just some neat little analogy. This concept of transformation is a fundamental principle that engineers use every single day to tackle really, really tough problems in both the physical world of hardware and the digital world of software.
So let's kick things off in the physical world. If you've ever looked at a complex circuit diagram, it can just look like a tangled web of spaghetti. Trying to figure out what's happening at any single point in that mess can be a real headache with all those interconnected parts.
So to untangle all that, engineers have this clever trick up their sleeve called source transformation. And the core idea? It's actually super simple and kind of brilliant. You can literally take a chunk of a circuit, say a battery next to a resistor, and swap it out for a totally different looking arrangement that, from the outside, behaves in the exact same way.
And hey, this isn't just some random hack. It's backed up by two heavy-hitting principles in electronics called Thevenin's and Norton's theorems. Basically, what these theorems guarantee is that no matter how ridiculously complicated a circuit gets, you can always boil it down to one of two super simple forms. They're like two sides of the same coin, and source transformation, that's just the practical way you flip from one side to the other to make your life a whole lot easier.
And the process itself is super practical. You just follow the recipe. You find the right pair of components, you do some quick and easy math using Ohm's law, something you learn on day one, swap them out, and then you tidy up the new circuit. It's a repeatable, almost mechanical way to just erase complexity.
And here's the magic. That messy, impossible-to-analyze circuit is suddenly clean and simple. To anything connected to it, it behaves exactly the same as before, but for you, the engineer, calculating what you need to know is now a piece of cake. You've changed the form to make the analysis easy without changing the function at all. Okay, so that's hardware, that's circuits, pretty cool. But what happens if we take that exact same powerful idea of transformation and apply it to the world of software, to code? Well, we can, and we do. In the software world, this is called a source-to-source compiler, but pretty much everyone just calls it a transpiler, and the name says it all. It's a special translator that takes source code and turns it not into the ones and zeros a machine understands, but into other source code. We're staying at that same human-readable level, just like we did with the circuit. And this is not a new thing at all. This has been going on for decades. Way back in 1978, Intel was using tools to automatically translate old programs to run on their new chips. By the 80s, these tools got even smarter, optimizing the code as they went. Fast forward to today, and that same idea has led directly to tools like TypeScript, which is absolutely essential for building modern websites and apps.
And just look at how vital this is now. A developer can write code in a newer, safer language like TypeScript, and the transpiler does the dirty work of converting it into plain old JavaScript that'll run in any web browser on the planet. Or think about this. You've got a massive, ancient codebase written in Python 2. A transpiler can automatically update the whole thing to modern Python 3. In every single one of these cases, the logic, the meaning of the program is perfectly preserved, only its form is changed to fit a new purpose.
So let's just put them side by side for a second. With circuits, the transformation is based on the laws of physics, like Ohm's law, and the goal is to keep the electrical behavior the same. With software, the transformation is based on the strict rules of a programming language, and the goal is to keep the program's logical meaning the same. You've got different rulebooks, physics versus logic, but the game is exactly the same. Create an equivalent, but way more useful, version of the original.
So why does all this matter? I mean, in the real world, what's the big deal? Well, it turns out this one big idea has a huge impact in two major areas: the hardware that powers our world and the software that runs on it. In hardware, these exact transformations are the magic behind things like digital twins. Think a full-on virtual jet engine that you can test on a computer before a single piece of metal is cut. This is also how engineers analyze our national power grids to make sure they're stable and to help prevent blackouts. And in software, transpilers are literally the engine that makes the modern web possible. They let developers use powerful, cutting-edge languages, knowing that the code will just work everywhere. It's a fundamental tool for managing both progress and complexity.
So when you boil it all down, it really comes back to this one powerful principle. Transformation lets us preserve meaning while changing form. And that isn't just a clever trick. It's a universal strategy for how we manage complexity, adapt to new technology, and keep building on everything that's come before us.
And that's what's so cool about this. We've seen how this one idea connects the very physical world of circuits to the very abstract world of code. So I'll leave you with this question. If this principle can simplify circuits and code, where else could it simplify our world?